These are the video notes for Objective 10 vectors. These notes correspond to sections 5.4 and 5.5 in your textbook. Before we begin with the mathematics of vectors, let's define what a vector is. You've previously seen that a line segment is a line starting at point A and terminating at point B, and is notated with a bar above AB. A ray, similar to a line segment, begins at point A in the direction of point B, but extends past point B. Well, a vector, if it's printed, is listed as a bold AB, but when we handwrite it, we notate it the same way that we notate a ray. The difference is that a vector terminates at point B. So A is considered the initial point, and B is considered the terminal point. Now, when we draw our own vectors, we tend to begin them at the origin. So point A tends to be 0, 0, and then point B is based on the components that we know about the vectors. Now, let's draw vectors that are just in space. Here is a vector from point A to point B. Vectors are defined as having both a magnitude and a direction. The magnitude is the length of the vector, and the direction is the angle formed with the horizontal. So for two vectors to be the same, they don't actually have to begin in the same place in space. This vector here, assuming that I've drawn it with the same magnitude and same direction, is considered equal to this vector here, since they can be translated to be on top of each other. There are a few forms of vectors that we need to be familiar with. So this is one way to notate a vector, but more commonly you're going to see a vector in component form. So this is considered component form, where this is x and this is y. This form allows us to graph a vector on a Cartesian plane. The last form that we need to be familiar with is the linear combination. So there are things called the unit vectors. We have I, and this is not the imaginary I, this is a bold lowercase I, being 1, 0. So this is the horizontal unit vector. And we have j being 0, 1. And since these unit vectors have a length of 1 with a horizontal and a vertical piece, all vectors can be rewritten as a linear combination of I and j. For example, AB would become AI plus BJ, since A is the horizontal component and B is the vertical component. So these things all mean the same thing. Now, how does trig relate to a vector? Well, everything we've done with complex form or trigonometric form of a complex number relates to vectors in a similar fashion. For example, if I were to draw the vector AB, and for the sake of this example, we'll assume A and B are both positive, I would draw it in quadrant 1, like so, and A would be the horizontal component, B would be the vertical component, and you can see that I've formed a right triangle. So if I use trigonometry and call the magnitude r, which we do call the magnitude of a vector r, I can say that the horizontal component x is equal to r cosine theta, since A is on the adjacent side. And B, being the vertical component, would be considered the opposite side, and so we could find the vertical component as r sine theta. And there we have the trig application, or the reason that vectors are considered an extension of trig, because its components can be broken down using cosine and sine. So the magnitude of a vector, if you're thinking about it in this context, is a formula we've seen time and time again. And we notate the magnitude of a vector the same way we notate the absolute value or modulus of a complex number. So the magnitude of a vector is equal to the square root of the sum of the squares of its component, which again is derived from the Pythagorean theorem, like many of our formulas to find the hypotenuse or the radius or the modulus or the magnitude. The last thing we want to talk about is how we notate vectors when they're not in the three forms. So in general, you'll see me reference a vector, and I'll be writing it in bold because with the whiteboard marker I can, but you can use it with the arrow across the top. So I can give you vector v, and then if I'm trying to reference vector v's components, I would refer to them as v sub x and v sub y. So that's just one more way that you can see a vector. With that being said, let's practice finding and converting vectors between their forms. So the first example I'd like to walk through is finding the magnitude of the horizontal and vertical component. Find the magnitude. And notice I'm not asking for the magnitude of the vector, I'm asking for the magnitude of the components. For a vector v, with magnitude 5.6 and a direction of 22 degrees. So if you consider graphing this, and you can actually find these components without graphing them, if you consider graphing it, 22 degrees is in quadrant 1, and we're basically saying the radius is 5.6. Well, I know the horizontal component is cosine, so I can write x equals 5.6 cosine of 22. And the vertical is sine, since it represents the opposite side. I can write y equals 5.6 cosine of 22 degrees. So all I need to do at this point to find the magnitude of these components is to, well, let's use the notation, Vx and Vy, is to calculate it. Make sure your mode is in degrees, which I'm checking on my calculator. And then simply type in 5.6 cosine 22. So Vx, or the magnitude of the horizontal component, is 5.192, and Vy, which is the vertical component of the vector, is 2.098. And so I can see that for a vector with 22 degrees, the horizontal component has a larger magnitude than the vertical component. For the next example, let's find the magnitude and direction of a vector that's already given in component form. Once you've found the components, it's really easy to write the vector in component form. You just set it up like an ordered pair using the triangle brackets that indicate vector. So I'd like to go the other way. I'll give you component form, and we will find the trigonometric magnitude and direction. So consider a vector 2, -6, and we'll call it v again using the bold. How can I find the magnitude and the direction of this vector? Well, the magnitude is my Pythagorean theorem. So the magnitude of this vector is the square root of 40, or 2 square root of 10. And then how do I find the direction? This is the exact same way I found the direction for a complex number. I like to get a graph. 2, -6 is here. 2, -6. Remember, your graph should always connect to the horizontal axis, not to the vertical axis. And then I need to find this angle. Since I have the opposite and adjacent sides, I'm using inverse tangent. Inverse tan of -6 over 2, or -3. Now I'd like my answer to be in quadrant 4, but the inverse tangent function is only defined from -pi-halves, or -90 to +90. I'm going to have to do some manipulation. I find that theta is equal to -72 degrees if I round to the nearest whole. Well, that's not in the fourth quadrant. So I'm going to find the coterminal angle by adding 360 degrees. The amount I add is going to vary depending on what quadrant I need my answer to lie in. So if we add 360 to this, we get that theta is approximately with some serious rounding, 288 degrees. And with that, I have found the magnitude and direction of the vector 2, negative 6. Okay, the last thing that we want to do is write a linear combination. So again, I mentioned at the beginning, we have two unit vectors, I and j. And every vector can be written as a linear combination of I and j by finding the horizontal component and the vertical component. So if I give you the vector -1, 7, and I ask you for the linear combination, all you have to do is rewrite it as -I plus 7j. And that's a linear combination of vectors. This concludes part 1 of the video notes for vectors. In this portion, we just introduced what a vector is and how we write it. In the next video, we're going to complete operations with vectors and see how they relate to the integer operations we're most familiar with.